Good morning, dear students. Today we will discuss about the power amplifiers. That is the topic of the analog electronics. So, in power amplifiers, we now discuss what is the power amplifiers, what is the application of power amplifiers, what is the advantage, disadvantage, and what is the working principles of power amplifiers. So, we will discuss these points by one. So there are some definitions related to the power amplifiers. So in small signal amplifiers, the main factors are first one is amplification, second one is linearity, and third one is the gain. So these are the factors of the small signal amplifiers, which is generally for the BJT, FET, and MOSFET. What since large signal or power amplifiers, so power amplifiers is the large signals amplifiers. They handles relatively large voltage signals and current levels. The main factors are of the power amplifiers. First one is the efficiency, second one is the maximum power capability, and next one is the impedance matching to the output device. So these are the factors of the power amplifiers. So amplifier types. So there are different types of power amplifiers. So first one is class A power amplifiers. In class A amplifier, the amplifier conduct through the full 360 of the input. The Q point is set near the middle of the load line. That is the class A power amplifier. Second one is the class B power amplifier. In class B power amplifier, conduct through 180 degree of the input. So the Q point is set at the cutoff points. So that is the class B power amplifiers. And next one is the class AB power amplifier. In class AB power amplifier, this is a compromise between the class A and class B amplifiers. The amplifier conducts somewhere between 180 degree and 360 degree. So the Q point is located between the midpoint and cutoff point. And next one is class C power amplifiers. The class C power amplifier conduct less than 180 degree of the input. So the Q point or quiescent point or operating point is located below the cutoff levels. Next one is the class D power amplifier. So in this class D power amplifier, that is biased especially for digital signals. So in class A amplifiers, the output of class A amplifier conduct for the full 360 degree of the cycle, and the Q point is set at the middle of the load line so that the AC signal can swing a full cycle. So in this figures, there is the power A amplifier operation in which a class DC bias level full 360 output swing, and next in figure, that is the so the IC versus VCE output current output voltage graphs. So here the Q point is the middle point of the load line. So remember that the DC load line indicate the maximum and minimum limits set by the DC power supply. What in class B amplifiers? A class B amplifier output only conduct for 180 degree, and we can see this in this figure in which the output conduct only 180 degree, that is the 180 degree output swing, and one half of the AC input cycle. In second figures, the Q point is at 0 volt on the load line, so that the AC signal can only swing for the one half cycle. So this is the process in class B power amplifier. This amplifier is a compromise between the class A and class B amplifier. So that is the class AB amplifiers. The Q point is above that of the class B but below the class A. We can also see in this figure also here. So the output conducts between 180 degree and 360 degree of the AC input signals. In class C amplifiers, the output of the class C conduct for less than 180 degree of the AC cycle. So the Q point or operating point is below the cutoff. Also we can see this in this figure also here. And next one is the amplifier efficiency. So what is the efficiency of the power amplifiers? So here we compare of amplifier classes. So we take the class A, B, B, C and D amplifiers, and first one is the what is the operating cycle. So operating cycle for the class A amplifier is 360, and for the class AB 180 degree to 360, and for class B operating cycle is 180 degree, and for class C operating cycle is less than 180 degree, and for class D amplifier operating cycle is pulse operation, typically over 90%. So next parameters is the power efficiency. So what is the power efficiency in class A amplifier? So that is the 25% to 50%, and power efficiency of class AB is between 50% and 25% and 78.5%, and power efficiency of class B is 78.5%, and efficiency of class D amplifier is typically over 90%. So class C is usually not used for delivering large amount of power, thus the efficiency is not given here. So efficiency referred to the ratio of output to input power. The lower the amount of conduction of the amplifier, the higher the efficiency. So that is the efficiency. Next one is series feed class A amplifier. So This circuit diagram is the series feed class A amplifier. In this circuit diagram is similar to the small signal amplifier except that it will handle higher voltage. The transistor used is a higher power transistor. So this is the series feed class A amplifier circuit diagram. Next, in this circuit diagram, when an input signal is applied, the output will vary from its DC bias operating voltage and current. We also can see this in this figure. A small input signal causes the output voltage to swing to a maximum of VCC and a minimum of 0 volt. The current can also swing between 0 milliampere to I, IC saturate, so VCC upon RCC. So what is the input power of the series feed class A amplifier? The input power into the amplifier is from the DC supply with no input signals. The DC current draw in the collector bias current ICQ. So PIDC input power DC equal to VCC into ICQ, where VCC is the DC voltage across the collector and ICQ is the collector current at the Q point. So next one is the output power. So output power P now DC equal to BC RMS square upon RC, or also P naught DC equal to BCE RMS into IC RMS. So P naught DC will be equal to I square C RMS into C. And what is the efficiency? So efficiency is P output AC upon P input AC into multiply 100. So this is the efficiency in percentage of the series feed class A amplifier. So this is the example in which calculate the input power, output power and efficiency of the amplifier for an input voltage that result in a S-base current of 10 milliampere if RV equal to 1 kilo ohm, RC equal to 20 ohm, beta equal to 25 and VCC equal to 20 volt. So we can find the efficiency and output power and of this circuit diagram with the help of these given data by using the given by these formula PIDC equal to BCC ICQ and output power P naught DC equal to I square RC and also efficiency equal to P output AC upon P input AC into 100. So we can easily find out these uh, factors by using the given data. So next one is the transformer upper class A amplifier. So in this circuit diagram, the this circuit is coupled by the transformer. So the coupling is the collector terminals in this circuit diagram. So this circuit uses a transformer to couple to the load. This improves the efficiency of the class A to 50%. So by the use of transformer coupling, we can improve the efficiency of the class A amplifier up to 50%. So here the transformer coupling in this circuit diagram. So voltage across the primary winding is V1 and voltage across the secondary winding is V2, and here V2 is equal to output voltage across the load resistance, and also N1 and N2 is the number of turns in the primary winding and secondary winding of the transformer. So a transformer improves the efficiency because it is able to transform the voltage, current and impedance. So voltage ratio here V2 upon V1 equal to N2 upon N1. So this is the relation between voltage and turn ratio of the transformer, and also what is the relation between the current and number of turns in the transformer binding. So this is the current ratio I2 upon I1 equal to N1 upon N2. And also what is the impedance ratio in this transformer coupled amplifier. So here RL equal to R1 upon R2 equal to N1 upon N2 का whole square or equal to A square. So this is the relation for the impedance of transformer coupled class A amplifiers. So what is the DC load line in transformer coupled class A amplifier? So from the this figure or diagram given here, so in this diagram class A amplifiers, the Q point is established close to the midpoint of the DC load line. The DC resistance is small, ideally at 0 ohm, and a DC load line is a straight vertical lines. This is the DC load line, and also in this graph, the AC load line for the transformer coupled class A amplifier. So AC load line, the saturation point IC max is at V alpha upon RL dash, and the cutoff point is at V2, the secondary voltage of the transformer. This increase the maximum output swing because the minimum and maximum value of IC and DCE are spread further apart. So signal swing and output AC power, the total voltage swing VCE peak to peak equal to VCE max minus VCE minimum. So here VCE is the voltage across the collector to emitter. So next is the current swing. So here IC collector current peak to peak equal to IC max minus IC minimum. IC is the collector current here. And what is the AC power? So AC power for this P naught AC equal to BCE maximum minus BCE minimum into BC maximum, sorry, IC maximum minus IC minimum divided by 8. That is the output AC power. Here VC is the voltage across the collector to emitter, and IC also collector current here. So power input from the DC source, so input power PIDC will be equal to BCC ICQ, and power dissipated as across the transistor. So PQ equal to PIDC minus P naught AC. Note the larger the input and output signal, the lower the heat dissipation. So power dissipated as heat across the transistor. And what is the maximum efficiency? So maximum efficiency in percentage equal to 50 into BCE max minus BCE minimum upon BCE max plus BCE minimum whole square. Note the larger BCE maximum and smaller BCE minimum, the closer the efficiency approach the theoretical maximum of 50%. Also, this is the another example. In this example, we calculate the efficiency of the transformer coupled class A amplifier for a supply of 20 voltage and output of 6 voltage. So here given output voltage and supply voltage, so we can easily find the efficiency, because efficiency is the output power upon input power. So here 12 divided by 6 equal to 2. And so we can easily find out the efficiency of this circuit diagram, which is given here. Next one is the class B amplifiers. In class B, the transistor is biased just off. The AC signal turns the transistor on. So the transistor only conduct when it is turned on by one half of the AC cycles. In order to get a full AC cycle out of a class B amplifier, you need two transistors. So a NPN transistor that provide the negative half cycle of the AC cycle, and PNP transistor that provide the positive half cycle. So this is the half cycle, one half cycle for the PNP transistor and one half cycle for the NPN transistors. And we can also measure the output across the load and the shape of the output voltage as shown in this diagram at the output across the load. So maximum efficiency of class B is 78.5%. That is the maximum frequency of the maximum efficiency of the class B power amplifier. So the efficiency in percentage equal to P output AC upon P input DC. So maximum output power DC equal to VCC upon 2RL. So for maximum power VL equal to VCC, and maximum input DC power is equal to VCC maximum into IDC. So this will be equal to VCC into 2 VCC upon pi RL, and will be equal to 2 VCC square upon pi RL. So this circuit diagram show the transformer coupled push-pull class B amplifiers, in which circuit diagram there is the three parts mainly. First one is phase splitting input transformer, that is the input side, and second is the push-pull circuit connections, in which two transistors Q1 and Q2 connected here. And next one is the push-pull output transformers. That is the at the output side. And next one is the a speaker we have as a load. So this is the transformer coupled push-pull class B amplifier circuit diagram. The center tap transformer used in this input side. So this produce opposite polarity signals to the two transistor inputs. The center tap transformer on the output combine the two halves of the AC waveform together. So during the positive half cycle of the AC input, transistor here Q1 is the NPN is conducting, and transistor Q2 that is PNP is off stage. And next, during the negative half cycle of the AC input, transistor Q2 PNP is conducting, and transistor Q1 that is NPN is off state. So each transistor through one half of an AC cycle, the transformer combines the two output to form a full AC cycles. So what is the crossover distortion? So in this figure, we can see here the crossover distortion that is indicated by a circle. That is the crossover distortion. If the transistors Q1 and transistor Q2 do not turn on and off at exactly the same time, so then there is a gap in the output voltage. So this is so the crossover distortion. Next one is the quasi-complementary push-pull amplifier. So this circuit diagram show the quasi-complementary push-pull A amplifier. A Darlington pair and a feedback pair combination perform the push-pull operation. So in this push-pull circuit diagram, there is the feedback pair also here. This increase the output power capabilities. So in this circuit diagram, the feedback pair combination increase the output power capability, and if the output of the amplifier is not complete AC sun cycle wave, then it is distorting the output. The amplifier is non-linear. So this distortion can be analyzed using Fourier analysis. In Fourier analysis, any distorted periodic waveform can be broke down into frequency components. These components are harmonics of the fundamental frequencies. So what is the harmonics in our amplifiers? So harmonics are integer multiple of a fundamental frequency. If the fundamental frequency is 5 kilohertz, for example, so what is the first harmonic? So first harmonic will be 1 into 5 kilohertz. And what is the second harmonic? So second harmonic will be 2 into 5 kilohertz. And third harmonic is 3 into 5 kilohertz. And fourth harmonic is 4 into 5 kilohertz, and etc. So note that the first and third harmonics are called odd harmonics, and the second and fourth are called the even harmonics. So there is both type harmonics present in power amplifiers, odd harmonics as well as even harmonics also there. So from these different waveforms diagrams, according to Fourier analysis, if a signal is not purely sinusoidal, then it contains harmonics. So if a signal is not purely sinusoidal, so then it contains harmonics or distortions. So in harmonic distortion, the signal is not pure sinusoidal signals. Now we find out the harmonic distortion calculations, and harmonic distortion D can be calculated. So percentage nth harmonic distortion equal to percentage Dn equal to An upon A1, amplitude of the An upon A1 into 100, where An is the amplitude of the fundamental frequency, and and An A1 is the amplitude of the A1 is the amplitude of the fundamental frequency, and An is the amplitude of the highest harmonic. Okay, so total harmonic distortion THD is determined by the in percentage equal to under root of D2 square plus D3 square plus D4 square and plus so on into hundreds. So in this power transistor dissipate a lot of power in a heat. This can be destructive to the amplifier as well as to surrounding component. So power in heat is very destructive, and it is not good for the amplifiers because it is it can be destructive the surrounding component also. Next one, class C amplifiers. So a class C amplifiers conduct for a less than 180 degree. In order to produce a full sine wave output, the class C use a tuned circuit or LC circuit or tank circuit to provide a full AC sine wave. So we use in this class C amplifier a tank circuit across the collector terminal. So tank circuit is the parallel combination of the inductor and capacitor. So that tank circuit provides the full AC sine wave to the class C amplifiers. And class C amplifiers are used extensively in radio communication circuits. So class C amplifier used in a communication, radio communication circuits. And next one is the class D amplifiers. In class D amplifier, amplify pulse and require a pulse inputs. These many circuits that can convert a sinusoidal waveform to a pulse. We can also see that conversion in given these two waveform diagrams, in which sinusoidal waveform is converted to the pulse to a sine wave. This circuit has application in the digital circuitry in which analog signal or sinusoidal signal is converted into the digital signal or pulse signals. Reference books. So electronics device and circuit by the Millman and Halkias. That is the reference books for this topic. Next one, there is some multi-choice questions, and now we will discuss these multi-choice questions one by one. The first question, the use of amplifier in a circuit is to for input signals. Option A, provide a phase shift. Option B, provide strength. Option C, provide frequency enhancement. Option D, make circuit compatible. So here correct answer is option B. The use of amplifier in a circuit is to provide strength for the input circuit. So here correct answer is option B. In next questions, the unwanted characteristics of amplifier output apart from the desired output is collectively termed as A, inefficiency, option B, damage, option C, fault, option D, distortion. So here correct answer is option D. The unwanted characteristics of amplifier output apart from the desired output is collectively termed as a distortion. So correct answer is option D. In next question, unit of power rating of a transistor is expressed in unit of power rating. So first watts, second be kilowatt hours, third one is the watt per second, and fourth D is the watt hours. So unit of power rating of a transistor, power rating. So power will be multiply of voltage and current. So power will be VI, P equal to VI. So unit of this power will be watts. So here correct answer is option A, watts. Which device was used for the amplification of audio signals before the invention of power amplifiers? Before the invention of power amplifier, which device was used for the amplifications? So here option A, diode, option B, op-amp, operational amplifier, option C, vacuum tubes, option D, SCR, silicon control rectifiers. So here correct option is C, vacuum tube, because before the invention of power amplifiers, the vacuum tubes devices was used for the amplification of the audio signal. Basically, amplification means increase the strength of the weak signal to a particular levels. So here correct answer is option C, that is the vacuum tubes. In next questions, the power amplifier directly amplifies power amplifier. Option A, voltage of a signals. Option B, current of the signals. Option C, power of the signals. Option D, all of the mentions. So in power amplifier, directly amplifies the option A, voltage of signal. That is correct. Second, power amplifier amplifies the current of the signal. That is also correct. And next one is power amplifier amplifies the power of the signal. So this this is also correct. So power amplifier directly amplified voltage of signal. Second, current of a signal. Third one is a power of the signal. So here correct option is the option D. In next questions, input stage of power amplifier is also called input stage of the power amplifier. Option A, first stage. Option B is the beginning stage. And third one is the front end. And option D is the normal stage. So input stage of the power amplifier is also called the front end. This is the input stage of the power amplifier. And correct answer is option C here. In next questions, a transistor in power amplifier is a transistor in power amplifier is option A, an active device, option B, a passive device, option C, a op-amp, option D, a voltage generating device. So transistor in use as a power amplifier is a active device because the transistor used as a power amplifier in active mode or as an active device. So here correct answer is option A. Transistor in power amplifier is a active device. Next, for a perfect power amplifier, output power rating will be if the output impedance is half. So option A half, option B is squared, option D doubled, option D is square rooted. So for a perfect power amplifier, output power rating will be half. Output impedance will be doubled. So this is the correct answer here, option C. The next questions. Which of the following audio speaker will be hard to the driven by a power amplifier? So here option A 4 ohms. This is the value of load. So in power amplifier, audio speaker is behave as a load. So here the load will be hard to the driven by the power amplifier. So what is the value of load? Option A is 4 ohm. Option B is 8 ohms. Option C is 12 ohm. Option D is 2 ohms. So here the correct answer is the option D, 2 ohms. So in power amplifiers, the audio speaker behave as a load resistance R. So the value of load resistance in power amplifier is the 2 ohms. So here correct answer is option D. Thank you. Thank you very much.